everyone, I'm Lorraine Marquinto from BS IT Department. For today, I'm going to discuss about a large-scale hierarchical multi-view RGB-D object datasets. The author of these are Kevin Lai, Leifing Bu, Xiaofing Rin, and Jeter Fox. Abstract. Over the last decade, the availability of public image repositories and recognition benchmarks has enabled rapid progress in visual object category and enhanced detection. Today, we are witnessing the birth of a new generation of sensing technologies capable of providing high-quality, synchronized videos of both color and depth, the RGB-D camera. Its advanced sensing capabilities and the potential for mass adoption. This technology represents an opportunity to dramatically increase robotic object recognition, manipulation, navigation, and interaction capabilities. This paper describes the dataset collection procedures and introduced techniques for RGB-D-based object recognition and detections, demonstrating that combining color and depth information substantially improves quality of results. Introduction. The availability of public image repositories on the web, such as Google Images and Flirt, as well as the visual recognition benchmarks like Caltech, LabelMe, and ImageNet has enabled rapid progress in visual object category and enhanced detection in the past decade. With its advancing sensing capabilities and the potential for mass adoption by consumers, driven initially by Microsoft Kinect. This technology represents an opportunity to dramatically increase the capabilities of robotics, object recognition, manipulation, navigation, and interactions. This image, each RGB-D frame consists of an RGB image, the left image, and the corresponding depth image is the right image. The bottom image, a zoom in a portion of the bowl showing the difference between the image resolution of the RGB-D camera and the point gray grasshopper. The RGB-D object datasets is a large dataset of 300 common household objects. The objects are organized into 51 categories arranged using WordNet hypername or hyponame relationships. This dataset was recorded using a Kinect-style 3D camera that records synchronized and aligned 640 by 480 RGB and depth images at 30 hours. Each object was placed on a turntable and a video sequences were captured for one whole rotation. For each object, there are 3 video sequences, each recorded with the camera mounted at a different height so that the object is a view from different angles with the horizon. Unlike many existing datasets such as Caltech and ImageNet, objects in these datasets are organized into both categories and instances. In these datasets, the class dog contains images from many different dogs, and there is no way to tell whether 2 images contain the same dog. While in the RGB-D object datasets, the category Sudakan is divided into physically unique instances like Pepsi Can and Mountain Dew Can. This dataset also provides ground truth pose information for all 300 objects. Here are some example objects that have been segmented from the background. In addition to introducing a large object dataset, we introduce techniques for RGB-D-based object recognition and detection and demonstrate that combining color and depth information can substantially improve the results achieved on our dataset. We evaluate our techniques at 2 levels. First, category level. Recognition and detection involves classifying previously unseen objects as belonging in the same category as objects that have previously been seen. Example, coffee and mug. Second, instance level. Recognition and detection is identifying whether an object is physically the same object that has previously been seen. The ability to recognize and detect objects at both levels is important if we want to use such as recognition system in the context of tasks such as service robotics. For example, identifying an object as a generic coffee mug or a Amelia's coffee mug can have different applications depending on the context of the task. The graphic shows that the fruit, device, vegetable, and container subtrace of the RGB-D object dataset object hierarchy. The number of the instances in each left category is given in parentheses that the shade in violet shows that several subtrays in the object category hierarchy. Fruit and vegetables are both top-level subtrays in the hierarchy. Device and container are both subtrays under the instrumentation category that covers a very broad range of man-made objects. RGB-D object dataset collections. The RGB-D objects dataset contains visual and deep images of 300 physically distinct objects taken from multiple views. The chosen objects are commonly found in home and office environments where personal robots are expected to operate. Objects are organized into a hierarchy taken from WordNet hypername or hyponyme relations and is a subset of the categories in an ImageNet. The dataset is collected using a sensing apparatus consisting of a prototype RGB-D camera manufactured by PrimeSense and a Firewire camera from Point Grey Research. The RGB-D camera simultaneously records both color and depth images at 640 by 480 resolution. In other words, each pixel in a RGB-D frame contains 4 channels: red, green, blue, and deep. The 3D location of each pixel is physically space can be computed using known sensor parameters. The RGB-D camera creates deep images by continuously projecting an invisible infirm structures, line pattern, and performing strangulations. Segmentation. Without any post-processing, a substantial portion of the RGB-D video frames is occupied by the background. We use visual cues, depth cues, and raw knowledge of the configuration between the turntable and camera to produce fully segmented objects from the video sequences. The first step in segmentation is to remove most of the background by taking only the points within a 3D bounding box where we expect to find the turntable and objects, based on the known distance between the turntable and the camera. This produce gives very good segmentation for many objects in the dataset, but is still problematic for small, dark, transparent, and reflective objects. Since depth-based and vision-based segmentation each excel at segmenting objects under different conditions, we combine the two to generate our final object segmentation. We take the segmentation from depth as the starting point. We then add pixels from the visual segmentation that are not in the background nor on the turntable by checking their depth values. Video scene annotation. The RGB-D object dataset also includes 8 video sequences of natural scenes. The scenes cover common indoor environments, including office workpieces, meeting rooms, and kitchen areas. The video sequences were recorded by holding the RGB-D camera at approximately human eye level while walking around in each scene. Each video sequence contains several objects from the RGB-D object dataset. The objects are visible from different viewpoints and distances and may be partially or completely included in some frames. These pictures example of segmentation. From left to right, bag of chips, water bottle, eraser, left vegetables, jar, marker, and pitch. Segmentation using depth only, top row. Visual segmentation via background subtractions, middle row, and combined depth and visual segmentation, bottom row. This pictures is a 3D constructions of a kitchen scene with a cup highlighted in a blue and a soda can in red using the labeling tool. In these pictures, in the top, ground truth bounding boxes of the cup, and the bottom, soda can, obtained by labeling the scene's reconstruction in this image. In this box shows that number of frames and objects in the 8 annotated videos of natural scenes in the RGB-D object datasets. The RGB-D mapping technique consists of two key components. First is spatial alignment of consecutive video frames. Second is globally consistent alignment of the complete video sequence. Successive frames are aligned by jointly optimizing over both appearance and shape matching. Appearance-based alignment is done with RENSEC over SIFT features annotated with 3D position. Shape-based alignment is performed through alliterative closest point using a point-to-plane error metric. The initial alignment from 3D SIFT matching is used to initialize ICP-based alignment. In this box means that category and instance recognition performance of various classifiers on the RGB-D object dataset using shape features, visual features, and with all features. Len SVM is linear. SVM key SVM is a Gaussian kernel. SVM RF is random forest. Object recognition using the RGB-D object dataset. In object recognition, the task is to assign a label or class to each query image. The possible labels that can be assigned are known ahead of time. State-of-the-art approaches to tackling this problem are usually supervised learning systems. A set of images are annotated with their ground truth labels and given to a classifier, which learns a model for distinguishing between the different classes. We evaluate object recognition performance at two levels. First, category recognition. In category level recognition, the system is trained on a set of objects. At this time, the system is presented with an RGB and depth image per containing an object that was not present in training, and the task is to assign a category label to the image. Example, coffee, mug, or soda can. And the second is in instance level recognition. The system is trained on a subset of views of each object. The task here is to distinguish between object instances. Example, Pepsi can, Mountain Dew can, or Aquafina water bottle. At this time, the system is presented with an RGB and depth image per the contents are previously unseen view of one of the object and must assign an instance label to the image. We subsample the turntable data by taking every fifth video frame, giving around 45,000 RGB-D images. For category recognition, we randomly leave one object out from each category for testing and train the classifiers on all views of the remaining objects. For instance recognition, we considered two scenarios. First, alternating continuous frames. Divide each video into three continuous sequences of equal length. There are 3 heights videos for each object, so this gives 9 video sequences for each instance. We randomly select 7 of these for training and test on the remaining 2. Second, leave sequence out. Train on the video sequences of each object where the camera is mounted 30 and 60 above the horizon and evaluate on the 45 video sequence. We average accuracies across 10 trials for a category recognition and instance recognitions with alternating continuous frames. There is no randomness in the data split for leave sequence out instance recognition, so we report number for a single trial. You can see this image. The red is a precious recall curves comparing performance with image features only, and the green is a deep features only, and the blue is both. The top row shows category level result. From left to right, the first two plots shows precious recall curves for two binary category detectors, while the last plot shows precision recall curves for the multi-category detector. The bottom row shows instance level results. From left to right, the first two plots shows precision recall curves for two binary instance detectors, while the last plot shows precision recall curves for the multi-instance detector. This three image shows that three detections result in multi-object sense. From left to right, the first two images shows multi-category detections results, while the last image shows the multi-instance detections results. As a features, we use a variant of histogram or oriented gradients (HOG), which has been found to work slightly better than the original HOG. Aside from HOG over RGB image, we also compute HOG over deep image, where each pixel value is the actual object to camera distance. That's all. Thank you.